Up to this point in the course, we have learned a lot about limits and a lot about derivatives. And then we've learned a lot about the applications for each. And now we're going to think backwards. And we're going to start talking about what's called antiderivatives. And the book calls it reverse differentiation. So now we're going to change our mindset and think we're going to be given the derivative now, and we're going to work backwards and find the original function. Now, something to take into consideration while we're doing this is that you can have a derivative that belongs to a family of functions. So what I mean by that is that you can have a derivative that belongs to many functions. If I gave you the function f of x is equal to 3x squared plus 7, and I gave you another function, we'll call it g of x, and that's 3x squared minus 2, and I give you another function, we'll call it h of x is equal to 3x squared plus 100. Now, if I take the derivative of f, I'm going to get 6x when I take the derivative of the term 3x squared. And then when I take the derivative of the constant 7, I just get 0. So my derivative for f is 6x. Now, when I take the derivative of g of x, for the first term, 3x squared, when I take the derivative, I get 6x. But then when I take the derivative of the constant, negative 2, I get 0. And for our last example, when I take the derivative of h, for the first term, when I take the derivative, I'm going to get 6x. And when I take the derivative of 100, I get 0. So if you notice, we have the same derivative, 6x, that belongs to all of these functions. So the only difference is the constant, and that is because when we take the derivative of a constant, you get 0. So when we work backwards, we have to take into consideration that there's a constant. So working backwards now, if I told you that f prime of x was equal to 6x, and I asked you to find the original function and work backwards, okay, so normally we take the exponent, bring it down, and multiply by the coefficient in front, and then decrease the exponent by 1. So we're going to do the exact opposite. I am going to increase my exponent by 1. So instead of having 6x, I'm going to have 6x squared. And then I'm going to divide by, instead of multiplying, I'm going to divide by the exponent. Instead of just leaving it at 6x squared divided by 2, I have to keep in mind that when you take the derivative, that constant disappears and we lose that value. So what we do is when we take the antiderivative, we add in a generic constant to remind us that there was a constant there. It could have been 0, but there was something there. So when I write my antiderivative and I simplify this, it's going to be 3x squared plus some constant. Now this is considered the antiderivative, and now we have a family of functions. I have 3x squared plus some constant. So there is an infinite number of functions that would represent that derivative, right? I could plug in any constant there. When I take the derivative, I get 6x. So when you're taking antiderivatives, you have to take into consideration that there was a constant and you have to add in that plus c. So now we're going to go through some examples of finding the antiderivatives. So we're given the derivative in this case, and we need to think backwards and find the original function. So with a power function, 3x squared, we can use the power rule, but we got to think in reverse. Normally with the power rule, when we take the derivative, we bring the exponent down in front and multiply by the coefficient. And then we decrease the exponent by 1. So now we got to go in reverse, and we got to add 1 to the exponent and then divide the leading coefficient by that exponent. So if we start off with our derivative, 3x squared, to get the antiderivative, we're going to add 1 to the exponent and then divide by the exponent. And then keep in mind that there is a constant there, so we're going to add in a constant. And then when we simplify that, we're going to get x to the third plus some constant. So this is the function. We'll use capital F for the function, and we'll use lowercase f for the derivative. So when I take the derivative of capital F, let's do a check. I would take the 3 down in front, decrease the exponent by 1, and then when I take the derivative of that constant, I'm going to get a plus 0, which is just 3x squared. So this works. So our answer for the antiderivative is this, and then this was our check to make sure it works. For part B, we have the derivative 1 over x. And if we think back to our derivative rules, and we can go back and look at our reference pages to remind us, when I take the derivative of a function that's natural log of x, we get 1 over x. So now working backwards, it's going to be natural log of x plus some constant. So now let's do a check. If I take the derivative of capital F, the derivative of natural log of x is 1 over x, and when I take the derivative of the constant, I get 0, and I'm just left with 1 over x. So that works. So this is our antiderivative. For the next example, we have that the derivative is cosine. Now, if we think of our derivative rules for trig functions, look on your reference sheet. If the derivative is cosine, find the original function. And if you look at your reference sheet, you're going to find that that original function is sine x, and then we have to add in that plus constant, and then let's check. If I take the derivative of sine, I'm going to get cosine x. And when I take the derivative of the constant, I'm going to get plus 0, so I'm left with cosine x. So that works. So this is our antiderivative. Last example, we're going to find the antiderivative of e to the x. Now, if you look at your reference sheet, you'll see that the original function would be, if I take the derivative of some function and I get the derivative e to the x, my original function is going to be e to the x, and then plus some constant. And then when I check it, when I take the derivative of my capital F function, the natural exponential function has the derivative of e to the x, and then you multiply by the derivative of the exponent, which is just 1 in this case. So I have e to the x, and then when I take the derivative of the constant, I get 0. So I'm left with e to the x, which is what we wanted. So this is going to be my antiderivative. Now we're going to look at the formal notation we use to represent antiderivatives. So this right here that looks like a stretched out s is called the integrand. And this here tells us that the variable that we're integrating is x. And when we take the antiderivative, we get our original function plus some constant. So we have to add in that constant. And if you scroll down here, we have some of the basic rules of integration, and we put them side by side here with the formula for taking the derivative. So for example, let's look at this here, just for an example. If I take the derivative of sine, I get cosine. So working backwards, when we do the antiderivative or we find the indefinite integral, I'm going to get sine x plus c. So here are some of those examples. Here's one that we just did in an example. When I take the derivative of the natural log, I get 1 over x. So when I take the antiderivative and I integrate 1 over x, I get the natural log of x plus some constant. So this will give you a chart that you can compare the differentiation formulas with the integration formulas. And this is all in your reference sheet as well. In the next couple of examples, we are going to verify an indefinite integral. So we're going to let this be our derivative. We'll call it f. And then we'll let this be our original function, and we'll call that capital F. So we want to verify that this indefinite integral is correct by showing that if I take the derivative of capital F, I'm going to get f of x. So I'm going to take the derivative of x squared over 2 plus e to the x plus our constant. Now, when I take the derivative of x squared over 2, I bring the 2 down in front. I decrease my exponent by 1. So that brings me from an exponent of 2 down to 1. When I take the derivative of e to the x, I just get e to the x. And when I take the derivative of our constant, we get 0. When I divide my 2's, I'm going to get x plus e to the x. And we just verified that this indefinite integral is correct. We got our lowercase f of x. So we're working backwards here, getting comfortable with this concept. Okay, next one, same thing. I'm going to call this function f, and then I'm going to call this function capital F. I want to show that if I take the derivative of capital F, I'm going to get my function lowercase f. So I'm going to take the derivative of x e to the x minus e to the x plus c. Now, when I take the derivative of the first term, x e to the x, I have to use the product rule. So I'm going to take the derivative of x, which is 1, and times it by e to the x, and then I'm going to add the derivative of e to the x, which is e to the x times x. Now, when I take the derivative of the second term, which is e to the x, I get e to the x. And when I take the derivative of the constant, I get 0. Now, when I clean this up and simplify, I can see that I have an e to the x here and a minus e to the x here. And those give me 0 when I add those up. And I'm left with just e to the x times x. And that's exactly what we got for our function f of x. So up to this point in this lesson, we've only focused on some real simple integrals with very basic functions. And now if we get anything that's more complicated, we're going to go through some properties of how you can handle that. So just like derivatives, we can break up the integrals for sums and differences of two different functions that are added together and you're trying to find the antiderivative. I can just add the antiderivatives together or subtract the antiderivatives together, depending on if it's a sum or difference. And then if we have a constant multiple in front, such as k, we just take k and multiply it by the antiderivative. So now we're going to work on finding the antiderivatives using these properties. So we have 4 terms here with addition and subtraction. And I can just find the antiderivative of each one and add them together. So I can rewrite this as the integral of 5x to the third dx minus the integral of 7x squared dx plus the integral of 3x dx plus the integral of 4 dx. Now I can also use that constant multiple trick and I can bring the multiple out in front. So I can rewrite this as 5 times the integral of x to the third dx minus 7 times the integral of x squared dx plus 3 times the integral of x dx plus 4 times 1 dx. When I work on the antiderivative for this first one, I get 5 times, and then I take the antiderivative of x to the third. So the antiderivative of x to the third would be if I increase my exponent by 1 and divide by that exponent. And then I add c. I'll call it c1 because we're going to have multiple c's here. When I look at this next integral, I have minus 7, and then I take the antiderivative of x squared. So that's going to be x to the third over 3. And then plus, I'll call this c2. For this next integration, I'm going to take 3 times the integral of x dx. So I add 1 to the exponent, and I divide by that exponent. And then I have plus c3. This next one, I have 4 times the integral of 1 dx. So that would be just x to the first, and then divided by x. Now, when I clean this up, I don't have any like terms. All of my x's have different exponents. So I'm going to write this as 5/4 x to the fourth minus 7/3 x to the third plus 3/2 x squared plus 4x. Now, when you deal with all these constants here, when I add those all up, I'm still going to have some arbitrary constant. So I'm just going to add those together and just call that c. In this next example, part B, we're going to integrate x squared plus 4 times the cubed root of x over x. Okay, so the first thing we're going to do to make this a little bit easier is we're going to split that up into multiple fractions and simplify each of those fractions. So for the first fraction, we're going to take x squared over x dx. Plus, then we have 4x to the 1/3 over x dx. Now, when we simplify this, we get the integral of x dx plus, and I can use that constant multiple rule and pull the 4 out in front, 4 times the integral of x to the negative 2/3 dx. So now when we go to integrate, let's do this one first. I'm going to integrate x and find the antiderivative, and then so I need to add 1 to the exponent and divide by the exponent. So I have x squared over 2 and then add my constant. When I look at the second integral, I have 4 times the integral of x to the negative 2/3. When I integrate x to the negative 2/3, I got to add 1 to the exponent and divide by that exponent. So that's going to give me x to the 1/3 divided by 1/3 plus my second constant. I can simplify this by writing 1/2 x squared plus, I do a flip and multiply, and I get 12x to the 1/3. And then when I add the two constants together, I have some arbitrary constant, and I'll call it c. So this will be our antiderivative for x squared plus 4 times the cubed root of x all over x. In our next example, we have the antiderivative of 4 over 1 plus x squared. And this I recognize as inverse tangent. That just comes with experience. If you don't know it offhand, just use your reference pages. I can rewrite this integral and pull the constant 4 out front and rewrite this as 4 times the integral of 1 over 1 plus x squared dx. And then I know that this is going to give me inverse tangent. And then when I have the 4 in front, that's going to give me 4 times inverse tangent of x. And then I have to add my constant. In this next example, part D, we're going to simplify this a bit before we start trying to integrate. With trig functions, sometimes it's easiest to simplify if you can first before you find the antiderivative. So if I rewrite tangent as sine x over cosine x, and then I have times cosine x dx, that will give me the integral of just sine x dx because I can cross off my cosines. One's in the numerator, one's in the denominator. So now I'm going to integrate sine x. So I'm working backwards. So look at your reference sheet and find what would give you sine x. Since I know that the derivative of cosine x is negative sine x, I can rewrite this integral with a double negative, so negative sine x dx. So I know when I integrate this, I get cosine x, and then I have that negative 1 in front, so my answer is going to be negative cosine x plus my constant. Okay, the last topic we're going to cover in this section is what's called initial value problems. Now, when you find an antiderivative of f and you integrate, what you're really doing is you're solving the equation dy dx is equal to some function. Basically, what you're doing is you're integrating both sides of the equation to find that antiderivative so you can find your unknown function y. So you're looking to solve for y. And when you solve equations like this is called solving a differential equation. And there's actually an entire class about doing just that called differential equations. When you solve a differential equation, it means that you're finding that function of f that you're looking for. And when you integrate, remember you come up with a plus c, that unknown constant. Well, in order to find that unknown constant, you have to have some additional information to plug in to figure out what that unknown constant is, and that's what's called an initial value problem. So when we're interested in determining a particular solution, so not just the whole family of solutions with the plus c, where that c could be anything, we need to know what that value of c is. And so we're given what's called an initial condition so that we can find that value of c. So initial value problems, we are given what's called the initial condition, which helps us solve for the unknown constant. Okay, our first example, we have dy dx, our derivative with respect to x is sine x. We're going to multiply both sides by dx, and then we're going to integrate both sides so we can solve for y. So I get y is equal to negative cosine x, and then I have plus my constant. So we have now as an answer that y is equal to this family of functions, negative cosine x plus some constant. That value of C could be anything. It could be 7, it could be 2, it could be -1,000,000, it could be -0.5. We don't know. So we have this whole family of functions. Now, we use what's called the initial condition to solve for our constant. So if we look up here, what's given is our initial condition. So we know that when x is 0, we get out that y is 5. So I can plug that in to solve for C. So I'm going to plug in 5 as y, 0 for cosine, and I can solve for C. So the cosine of 0 is 1. And then I have that negative in front, so I get 5 is equal to -1 plus C. When I add 1 to both sides, I get that C is equal to 6. So now I know the specific function. That we were looking for because we were given that initial value. So our final answer is going to be y is equal to negative cosine x plus 6. In this last example of the lesson, we are going to go through an application of antiderivatives. And the problem reads, a car is traveling at the rate of 88 feet per second, which is 60 miles per hour, and the brakes are then applied. The car begins to decelerate at a constant rate of 15 feet per second squared. The first thing we need to find out, part A says how many seconds elapse before the car stops. And part B says how far does the car travel during that time. So the first thing we need to do is determine what our variables are going to be. Let's let t be the time in seconds after the brake is applied. So that means that t equals 0, the brake is applied, and if it's t equals 2, then that means it's 2 seconds after the brake has been applied. Okay, we're going to let a of t be the acceleration, and we're going to let v of t be the velocity, and this is going to be in feet per second squared because it's acceleration, and this is going to be in feet per second. We're going to let s of t be the car's position, and that's going to be in feet, and that's going to be past the point in which the brakes were applied. So for example, if the position function says 3 feet, that means when the person driving the car stepped on the brake, they have moved 3 feet after they have pressed on the brake. So since the car is traveling at a rate of 88 feet per second, we know that the velocity at that point when he steps on the brake is going to be 88 feet per second. So we can say that v of 0 is 88 feet per second. The problem also told us that the acceleration was 15 feet per second and it was slowing down. So we're going to use a negative to indicate that it's slowing down. So a of t we're going to list as negative 15 feet per second squared. This tells me, since we know that the derivative of the velocity is acceleration, this tells me also that v prime of t is negative 15 feet per second squared. So I have two pieces of information here now that's important. I have the derivative of v here is negative 15, and I also know that at the starting point, the velocity was 88 feet per second. So to find my velocity, I'm going to integrate. So I'm going to have the derivative of v with respect to t is equal to negative 15 Now, when I multiply both sides by dt, then I can integrate both sides to solve for v. When I do this, I get v is equal to negative 15t and then plus some constant. Since I know that when t is 0, the velocity is 88 feet per second, that was given here. I'm going to highlight it again in another color because we really need to recognize that. If I plug in t is 0, I should get out 88 feet per second. My constant is 88. So now to answer the question, how many seconds elapsed before the car came to a complete stop? If the car is at a complete stop, the velocity is 0, and we can solve for t. And that will give us the time in seconds since they hit the brakes. So when I solve this for t, I'm going to get 88 over 15 seconds. And we can approximate that. 88 divided by 15 is approximately 5.87 seconds. So it took the car about 5.87 seconds to come to a complete stop after they hit the brakes. Okay, part B says, how far does the car travel during that time? So we need to figure out the distance using the position function. So now we need to use the velocity function and integrate it to find the position function. I know that s prime of t is equal to the velocity, which is equal to what we just found, negative 15t plus 88. So I have that ds dt is equal to negative 15t plus 88. I'm going to multiply both sides by dt, and then I can integrate both sides and find the antiderivative. So that gives me that s, which is our position function, is going to be negative 15t squared over 2 plus 88t plus some constant. Now, even though the problem didn't tell us this, we do know that for the position function, at time is equal to 0, the car hasn't moved any distance yet. So we have the point 0, 0, and we can use that to find our constant. So if I plug in 0 for my position, and I plug in 0 for my time, I'll find that the constant is just going to be 0. So my function, s of t, is going to be negative 15t squared over 2 plus 88t. Now, if we want to figure out how far the car has traveled before the car came to a stop, we knew that took 88 over 15 seconds, which is approximately 5.87. So we can put in 5.87 seconds in for t and find out how far the car traveled when it came to a stop. So I'm going to plug in 5.87, and we are going to get approximately 258.13325 feet. So after 5.87 seconds approximately, the car comes to a stop and it's traveled 258.13325 feet.